we're going to look at the derivatives of inverse trig functions. So I wanted to remind you how we find the derivatives of inverse functions in general. If we have an inverse function f inverse and we want to calculate its derivative, we're going to calculate 1 over the derivative of the function f, but instead of evaluating at input x, we're going to evaluate at f inverse of x. Okay, we're going to try this out where f of x is equal to sine x on its domain, on its normal restriction, so negative pi over 2 to pi over 2. Here, f inverse is going to be the inverse sine function, or arcsine. Okay, and so using our formula here, the derivative of f inverse is 1 over the derivative of f. Derivative of f is just cosine x. So we're going to take cosine, and we're going to evaluate it at f inverse of x, which is the inverse sine x. And you can see now why we've been practicing how to simplify compositions. This is one composition we're going to try and simplify. So we've got cosine of the inverse sine of x. Let's let theta be equal to the inverse sine of x. So sine of theta is equal to x. And what we would like to do is evaluate 1 over cosine of theta. So we worked this out earlier. I'm just going to run through it one more time a little bit quickly. So we're going to build a reference triangle for theta. So a right triangle with an angle theta. We know sine of theta is supposed to be equal to x, so the ratio of the opposite side over the hypotenuse should be x. We then use the Pythagorean theorem to fill in the missing side. So we get square root of 1 minus x squared. And we know cosine is positive, so if we were worrying about the sign of this, we would choose just the positive square root of 1 minus x squared. Okay, and looking at this triangle, we see that cosine of theta is the adjacent over the hypotenuse, which is square root of 1 minus x squared. So the derivative of the inverse sine function is equal to 1 over the square root of 1 minus x squared, for x. You can see if we the inverse sine function has domain negative 1 to 1. But if we were to plug in either 1 or negative 1, this derivative doesn't make sense. So this is going to be true for x in negative 1 to 1, not including the endpoints. Okay. So our inverse sine function's derivative is given as 1 over the square root of 1 minus x squared. We're going to try this out another time by looking at the derivative of the inverse cosine function. Okay, so here we're going to imagine that f of x is cosine x, and it's on its restricted domain. So x is going to be in 0 to pi. Okay, So the range of this function is going to be negative 1 to 1. Okay, so if we want to calculate the derivative of cosine inverse x, it's going to be 1 over the derivative of cosine evaluated at cosine inverse of x. Derivative of cosine is negative sine. So we have 1 over negative sine of inverse cosine of x. Okay, and we're going to simplify this composition by calling the inverse cosine x theta. So we would like to know sine of theta. I'm going to bring this negative sign up. We want to know negative 1 over sine of theta, where theta is equal to the inverse cosine of x, because the outputs of inverse trig functions are going to be angles. So if theta is the inverse cosine x, then cosine of theta is x. And theta is in 0 to pi. Okay, well, we can build a reference triangle for theta. So a right triangle, we have this angle theta marked. The ratio of the adjacent over the hypotenuse needs to be equal to x. So one easy way to make this happen is by using x and 1 as the adjacent and the hypotenuse side. We can look for our missing side length. This is going to be the square root of 1 minus x squared. Okay. And then we're going to take the sine of theta, which is going to be the ratio of the opposite over the hypotenuse side. So this is going to be the opposite over hypotenuse, or square root of 1 minus x squared over 1. And so our derivative simplifies down to being negative 1 over the square root of 1 minus x squared. So it's almost identical to the derivative of inverse sine. This is negative the derivative of inverse sine. Again, we're going to see that the inputs are just negative 1 to 1. It's not defined at the ends. Good job. Okay, we've got one last one. We're going to find the derivative of arctan x, or the inverse tangent function. So here f of x is equal to tangent of x, and f inverse is tan inverse. Using our formula, the derivative of the inverse tan function is going to be 1 over the derivative of the tangent function, where we're going to be evaluating at the inverse tan function. Derivative of tangent is secant squared. So we've got secant squared of tan inverse of x. And this is often a little bit easier to think of as 1 over secant squared of theta, where theta is the angle produced by the inverse tan function. So tangent of theta is equal to x. And we would like to know what secant squared of theta is. If we just knew secant, we could square that, and that would tell us. Okay. So we're going to, again, build a reference triangle. We put in our angle theta. Tangent is the ratio of the opposite over the adjacent sides. So one way to have a ratio of x is to make the opposite side x and the adjacent side 1. And this one will work out, and then we can use our Pythagorean theorem to fill in our missing side lengths. We've got 1 squared plus x squared is the square of the hypotenuse. And so we have all of our side lengths filled in. Secant theta is 1 over cosine theta, which is the hypotenuse over the adjacent side, or square root of 1 plus x squared. If we square this, secant squared theta is going to just be 1 plus x squared. And what this means for us is that the derivative of tangent is equal to 1 over 1 plus x squared. Good. Next, we're going to summarize.